Hi, my name is Samuel, and today on DSA we will be discussing string matching in finite state automaton. A finite state automaton, or finite state machine, is a mathematical model of computation that can be in one of a finite number of states and can transition from one state to another when a condition occurs. The behaviors of these finite automaton can be observed in devices such as traffic lights or lifts, receiving input and going to the relevant floor or the state. A finite state machine consists of a tuple. Q is a set of finite states. Q0 is the initial start state. Sigma is the finite input alphabet. Delta is the transition function, and F is the finite set of accepting states, and F is a subset of Q. The general idea here is to search through a string and check to see whether the desired sequence of characters exists as a substring of this string. If we want to program this in a language such as C or Java, we would want to implement something like this. Here, we simply search through the string and the character at the index of the string. If it matches the first character of the substring, then we increment x, and if not, then we reset x to 0. Upon reaching the end of the string, if x, the number of characters that have matched, is the same as the substring's length, then we know that we have found the substring in the string, and therefore we return true. Otherwise, we will return false. Now, sigma and delta. Let's start by matching the string A, A, B, C. Now, in this case, the alphabet is A, B, and C. The transition function is defined as follows, where Q and Q prime are both elements of the set Q, and Y is an element of the set sigma, or is a letter in the alphabet. So here we diagrammatically represent this transition function. Say we want to match a string AAB, ABC in any given string with the alphabet A, B, and C. Now, we've already gone over how to do this in pseudocode, but to use a finite state automaton, we would have to draw a diagram like this. For example, the idea is we start in Q0, and if we read an A, which is the first character in our chosen substring, we will transition to state Q1. Otherwise, if we read a B or a C, we stay in state Q0. Once in state Q1, if we read another A, which is the second letter of our chosen substring, we will transition to Q2. And there, if we read a B, an A, a B, and a C, in that order, we will then reach Q6, which is our accepting state. Along that line, if we read any other character that isn't a part of our substring in the order, then we will go back to state Q0, as that string is not the one that we are looking for. So we must therefore start from the beginning to match this substring. Much like the pseudocode when we reset x to 0 if we read another character that isn't part of our sequence in our substring. Now I'll go through this process step by step with a given string. The start state is Q0, and we read the first character in the string and match it to the substring. Here it is an A, so we transition to Q1. Now we're in Q1, and we read the second letter of the string, which is also an A, so we transition to state Q2. In state Q2, we read the third letter in the string, which also matches our substring, so we transition to state Q3. Now, in this state, we want another A to match our string, our substring. However, we read a C, therefore we must go back to state Q0 and we must start again. We read another A and transition to state Q1. Now in state Q1 we read another A and transition to state Q2. In state Q2 again we read a B, transition to state Q3. In state Q3 we read another A, so transition to state Q4. In state Q4 we read another B, matching our substring, and transition to state Q5. And in state Q5 we finally read a C, matching our substring, and move to the accepting state Q6. Now in this accepting state Q6 we can read any of the A, B or C from the alphabet and remain in our accepting state, as we have already found that the string contains our substring. Now the important things to note here is that concentric circles in a diagram represent accepting states. So if the machine is in any of these states, then it will accept. However, if it's in any other state, then it will reject that input. We will now go on to another example where the machine rejects. Here we begin in Q0 once again, and the first character in the string is red. Here it is an A, so we progress to state Q1. In state Q1 we read a B, which is not part of our substring, so we must return to state Q0. Again in Q0 we read a B and must remain in this state. We then read a C. Our substring does not begin with a C, so we must remain in state Q0 again. Then a B is read and must remain in state Q0. We can only progress to state Q1 if an A is read. The next character in the string happens to be an A, so we can now progress, transition to state Q1. In state Q1, to transition to state Q2, we must read a C. However, the character read in the string is an A, so we must return to state Q0. Finally, in state Q0, we read a C and must remain in state Q0. Now here, as state Q0 doesn't have concentric circles, it is not an accepting state, so our machine will reject. In our pseudocode representation, this would be equivalent to returning false. Our substring has not been found in the string. Another important thing to note here is the big O notation, the complexity of this algorithm. Now, the complexity of this algorithm is in order ON. As the input grows, so does the maximum number of checks required to match the substring. This can also be seen from the pseudocode, the outer loop. For I is equal to 0 to n, this code will run from 0 to n with a maximum of n iterations. This further confirms that this algorithm is in the order ON. This has been Finite State Machines for String Matching. Thank you for watching. Peace.